Welcome to the post-class video on titrations. Big topic, complicated topic, and so we're going to go through kind of a complicated example and try to take you through all the steps. And so the problem has to do with lactic acid. Like lactic acid is a buildup in
produced in your muscles.
Yeah, your muscles, right? You do a lot of anaerobic activity, you build up lots of lactic acid, and it causes soreness. And so there are actually, people have done studies about, how much lactic acid builds up over time. They want to find out how much. So this is kind of, the setup.
All right.
And so we have a sample that's 25 milliliters, and it has some lactic acid in it. And we're going to find out the concentration by titrating with 7.53 milliliters of 0.1007 molar sodium hydroxide. Of course, before we do the titration, we don't know what the volume is, but they did.
Right.
That's what they found. Okay. So the two questions are, what is the concentration of HA? And the second is, what's the pH at the end point? Okay, so what's the concentration of HA? And so when that question is asked, it's always asking about what's the concentration of the acid in the original solution.
Right.
Okay? So what's the first step? Whenever we have a chemical reaction, what do we have to do?
Write up the reaction.
Write up the reaction. And I'm going to make it a little bit simpler. I don't want to write out the formula for lactic acid because guess what? All the carbons and most of the hydrogens don't matter.
Right, it's that one hydrogen that's...
It's that one hydrogen. The one thing I do want to make sure is that it's monoprotic acid.
Right.
And so I look on my little sheet and I find lactic acid. Oh, it's a monoprotic acid. Only one hydrogen is coming off. And so I can abbreviate it HA. Great. And it's reacting with sodium hydroxide. Strong base reacting with a weak acid. It's quantitative, so I'm not going to draw a reversible arrow there.
Right, it's going to go all the way forward.
Yep, just stoichiometry. And what do I make? I make sodium A- base and H2O. And I probably ought to put AQ here and AQ there. Okay. So there are two ways that you can do this. You can do this long way by going through stoichiometry and saying, okay, I have 7.53 milliliters. If I want to get to moles, I multiply by the concentration. And then that gives me moles of base. It's a 1-to-1 ratio. So if I know that, guess what?
It's the same number.
It's the same number as moles of acid. And then if I want to know concentration, I know moles, I divide by volume. Divide by 25 milliliters, the volume.
Right.
So that's the long way around, and if you have not a 1-to-1 ratio, that's probably how I would do it, because I always get confused.
Right.
Since it is a 1-to-1 ratio, we can use the simpler form. MAVA equals MBVB.
Right.
Pretty simple. Do I need to put in the numbers to show? Do the calculation, check it on your own, and make sure that what you get is concentration of HA equals 0.0300 molar.
Right.
Original concentration. Does that make sense? This concentration is less than the concentration of the base. Does that make sense?
Yes, because the base is stronger.
Yeah, because the base is stronger, and so we don't have to use as much volume. Right? There's more concentrated, you don't use as much volume. So that kind of makes sense. Okay, so the second question, what is the pH at the end point? So what's in the flask at the end point?
Well, at the end point, we have some of this, some of that.
Exactly. At the end point, we've added exactly as much sodium hydroxide as lactic acid, and so these two are completely reacted. They're all gone. All I have left is this, right? That's a salt solution, right?
Right.
What do we know about sodium?
It's a spectator.
Spectator ion. What is A?
A was our lactic acid.
Right?
Right, and we know that because it's a weak acid, it also forms a conjugate base.
Yep. It's the conjugate base of our lactic acid. And so what we have here is a base hydrolysis problem.
Right.
Okay? So we're going to move over to the other board and work through this base hydrolysis problem.
All right.
Okay. So from that other problem, we have that we started out with 0.0303 molar lactic acid, and we had 25 milliliters, and we had 7.53 milliliters of sodium hydroxide. So we want to set up the base hydrolysis. We know that we have A minus.
Right.
And what's the base hydrolysis reaction?
That it would get added to water.
Yep, the aqueous gets added to water.
And therefore form hydroxide.
Hydroxide.
Because it's a base, right? And then A and AH. Right. You get some of that HA back.
Yep. Okay. And base hydrolysis, we're going to assume we're starting off with none of that, i.e. we are starting at the end point of the reaction.
Right.
This is a pure liquid, I'm not going to worry about that. And so the key is, what am I going to use for the concentration of A minus at the beginning of this? Right? You might think that, well, HA minus, there's as much A minus as you started with. You might say it's 0.0303 molar.
Right.
But you'd be wrong.
Oh, no.
Right? You have the same number of moles, but guess what? The volume has changed.
Oh.
Right?
Right.
So how do we figure out the concentration of this stuff?
Well, we would use the number of moles in the new volume.
Yeah, we use the number of moles of this stuff in the new volume.
We can use M1V1 equals M2V2.
We could use M1V1 equals M2V2, i.e. treat this as a dilution problem. We're taking this many moles and diluting it from 25 milliliters to, what is that, 32.53 milliliters. Right, and so I'll write this out here.
Right, and we're solving for M2.
Yep, and you do that and you find out that it is...
Right, which is different from what we had before, so it's a good thing that we accounted for dilution.
And it's a little bit less concentrated, right, because we diluted it. Now it's simple. So here's our ICE table, and I set up my equilibrium expression, the products over the reactant equals K.
Right.
So what am I going to put in for K?
Well, for K, we're using a base problem, so you can't use Ka. You would need to find Kb.
Okay. So Kb, I want to put Kb in there. What is Kb? It's Kw over Ka.
And we know what the Ka is because we can look on our little sheet and find Ka.
Right. And we always know Kw is 10 to the minus 14. And Ka, I looked it up on the chart, it's 1.4 times 10 to the minus 4. And this becomes, you know, our standard little old equilibrium problem. And I can see I might get a quadratic unless I assume that goes to 0.
Right.
And if I look at this, I'm going to get a number around 10 to the minus 10, so I know my Ka is going to be small.
Right.
Right? So you can do this math out. And when you do, you find that x equals 1.29 times 10 to the minus 6 molar.
Right, and don't forget, this is the concentration of our hydroxide ions.
Yeah, exactly.
Right? Not the concentration of our H. So we can't use this to find pH directly. Right? We have to go around the rectangle.
Yep. Yep. So just to be clear, that equals concentration of OH minus, right? Because that's what X is.
Right. And
so the way I did it, I calculated POH by taking the negative log of that, and I got 5.889, subtracted it from 14, I I've got pH equals 8.11. pH equals 8.11. So this weak acid being titrated with strong base, our endpoint isn't pH 7 neutral, it's just a little teeny bit basic.
Right, and that's because we have that conjugate base.
Yep. So that's a lot of different things all in this one problem. And partly, you know, you just got to recognize some problems are going to be a lot of different steps. Do the pieces that you can, one piece at a time. And don't be afraid if you don't see the whole thing right away, right? Just take it one step at a time, and maybe by the time you finish one step, you'll see the next one.
Right. And we see a lot of those skills that we learned coming back. We have our ice tables, our old friend, equilibrium constants, and then how we calculate for pH. So we need all those skills when we start moving on.
Exactly. So hope this helped, and good luck.